Okay, so we have a pleasure to listen to new lecturer, L.Vandenberghe. Okay.
Thank you. Thank you for the invitation. It's an honor to give a lecture in a course organized by Upravlение. So I'll start by explaining the words in the title. So I think most of you know what a semi-definite programming problem is. So you have a symmetric optimization variable x that has to be positive semi-definite. And then you have a linear equality constraint on x and a linear objective function. So you express them as a trace of a symmetric matrix times x, and that's called an SDP. So it's a problem that has attracted a lot of attention for more than 20 years, and in large part it started with a book by L.Vandenberghe, because they showed that by extending the proper concepts, you could generalize polynomial time methods for linear programming to semi-definite programming, if you define the correct barrier function and a central path and develop it and so on. It has many applications, and maybe the most important ones today are first that it's used in convex modeling systems, and it also goes back to the work by L.Vandenberghe, because they pointed out that many nonlinear convex functions could be represented in terms of semi-definite programming problems. And that actually has evolved then into software systems that uses observation to solve general convex optimization problems. So almost every time you use CVX to solve an optimization problem, it actually converts it to an SDP and solves an SDP. So a very large number of SDPs are solved all the time, but it's transparent and it's not always clear to the user. Second, a large class of problems is relaxations of quadratic optimization problems and polynomial optimization problems. So if you take the Lagrange dual of a general quadratic optimization problem with a quadratic objective and quadratic constraints, then you get an SDP. So an SDP, even if the original problem is not convex. So it can be used to compute or solve relaxations of non-convex quadratic problems and also polynomial problems. So in many of these applications, the coefficients are very sparse. So the coefficients AI and C are very sparse. But exploiting, for example, in relaxations of combinatorial problems, sparsity often reflects some network structure in the underlying problem. For example, if it's a graph partitioning problem, then the relaxation will have some sparsity that's related to the graph that we're partitioning. And also many of the other types of applications have actually a lot of sparsity in the coefficients AI and C, but it is much more difficult to exploit sparsity in semi-definite programming than in linear programming. And part of the problem is that in general, even if the coefficients C and AI are very sparse, X has to be a full matrix. You have an n by n matrix, so n squared over two variables, and in general they all have to be non-zero to be feasible, even if the coefficients are very sparse. So if the coefficients are sparse, then only if those entries in X appear in the objective function and the constraint, but to make it positive semi-definite, you may have to make the entire matrix non-zero, and also at the optimum typically it's non-zero. So that's part of the reason why it's difficult to exploit sparsity in semi-definite optimization, and it's still an ongoing research topic. So this talk will be about sparse semi-definite programming. There are different approaches that exist, so we'll talk about 2 and 3 in this list. So the second one is tries to exploit this fact that if the coefficients are very sparse, only those entries of X that are multiplied with non-zero coefficients appear in the objective and the constraints. And the other ones are only needed to make it positive semi-definite. And that can be used in non-symmetric interior point methods, as we'll see, and it's related to matrix completion in linear algebra. And a third approach then is to try to exploit sparsity for decomposition, to be used in interior point methods or first-order methods. So that's semi-definite programming. So Chordal graphs is a subject or a type of graphs that have been studied since the late 50s at least, or the 1960s. They have been studied in many different areas, often under different names and independently, and some of the results have been reinvented or rediscovered several times. So in linear algebra, they appear in sparse factorization algorithms. So Chordal sparsity pattern, or Chordal graphs describe the sparsity pattern of matrices that can be factored without filling by Cholesky factorization. It also appears in completion problems, as we'll see. So this is most closely related to the semi-definite programming and also the reason why we're interested in. In combinatorial optimization, that's actually maybe the first use of Chordal graphs. They're known as examples of perfect graphs. And perfect graphs are graphs for which a list of problems that are very difficult in general are actually very easy. For example, enumerating all the cliques in a graph is very difficult in general, or finding the largest clique in a graph. But for Chordal graphs, it's actually very easy, and you'll see that how you can find all the cliques in a Chordal graph very easily. In machine learning, they are known as decomposable graphs also, and they appear in graphical models and contingency tables and also Euclidean distance matrices. In nonlinear optimization, they've been studied in connection with partial separability and just nonlinear optimization. There are problems in computer science and database problems that give rise to Chordal graphs and so on. And they were first used in semi-definite optimization methods around 1970. So the two lectures will probably have this outline. So today we'll talk about the basic theory of Chordal graphs, just the basic, will be an introduction to Chordal graphs and the basic results, and then how they appear in sparse matrix theory. And then at the end of the second part, we'll see how they are connected to semi-definite programming. And then in the second lecture tomorrow, depending on how far we get today, we'll cover 2 or 3 applications to non-symmetric integral point methods or decomposition, and also how they are important for relaxations. So Chordal, first some notation for graphs. So we denote an undirected graph in the standard way. We have a finite set of vertices and a set of edges. And edges are undirected, and we denote them by set notation. So it's a pair of exactly two elements. Just to emphasize that the edge VW is the same as the edge between W and V. You have no cell groups and so on. If they're connected by an edge, they're adjacent, and the neighborhood, we'll use this notation for the neighborhood, or the adjacency step of a vertex. It's all the vertices adjacent to V, and sometimes we will use the term closed neighborhood for the neighborhood plus the vertex V itself. A subgraph is a subgraph induced by a subset of the vertices. Is the graph with those that subset of the vertices as its vertex sets, and also all the edges from the original edge set that connect to vertices in that set W. So we call that the subgraph induced by W, or just usually the subgraph W. W is a set of vertices. And it's this is an important remark, so we'll distinguish between complete subgraph and clique. So clique in this talk will always refer to a maximal complete subgraph. And many papers also use clique for just a complete subgraph, and then a maximal clique if it's a maximal complete subgraph. So here I'll use clique only for a maximal complete subgraph. So in this example, the subgraph induced by these 4 vertices, A, B, C, D, would be those 4 vertices and then the 4 edges. So you take out C and all the edges connected to C. The subgraph AB is a complete subgraph, but it's not a clique, and ABC is a clique because it's a maximal complete subgraph. And then later, when we apply to symmetric matrices, we'll use graphs to describe a sparsity pattern. So in that application, the vertex set will be the indices of the rows and columns in the matrix. So V will just be the set 1 through N. And the edges have the following meaning. If ij is an off-diagonal entry, and it's not an edge in the graph, then in that position of the matrix A you have a 0. So if that's the case, we say that A has the sparsity pattern E. So the other edges on the diagonal, or the other coefficients on the diagonal, And in the off-diagonal positions where there is an edge, can be 0 or non-zero. They don't have to be 0. So that also means that a sparsity pattern is not unique. If a matrix has a certain sparsity pattern, for example, this matrix has this sparsity pattern, for example, because in position 4, 1 there is no edge, so that entry is 0. Then you can also add an edge in this pattern, and it's still a correct sparsity pattern for this same matrix. Because it just says something about entries that have to be 0, the other entries may or may not be 0. And then the cliques in the graph will correspond to dense principal submatrices in the matrix. For example, 1, 2 is a clique, so that's this dense principal submatrix. And again, it's dense with the same comment that it doesn't necessarily mean that all these entries have to be 0. Right? That's possibly non-zero. But that's for the next part of the talk, actually. So I think everybody knows what a tree is. So you can characterize a rooted tree, of course, by specifying its parent function. And then we also sometimes use parents or ancestors of higher order. So if the parent of a vertex is f, then its grandparent or its second order parent is written like this. P squared h would be b, and then p cubed would be the root, and so on. A topological order is an ordering of a tree in which you visit each vertex before its parent. So this is an example of a topological order because each vertex has a lower index than its parent. And an example of a topological order is a post-ordering. And in a post-ordering, all the descendants of a vertex have consecutive numbers. For example, all descendants of this vertex with index 9 are numbered 6 to 8. And you can find a post-ordering by just going through the tree in a depth-first order. So in this case you have 10 vertices, so you start with 10 and then you assign the labels in a descending order in depth first search order. Right? So you assign 10, 9, 8, 7 for example, then 6, 5 and so on. And a post ordering is very convenient because some questions become very easy to answer. For example, if you compare vertex H and D, and by just knowing the labels and the fact that D has 3 descendants, you know that H is not a descendant of D. Because they're numbered consecutively, so this has been. Okay, so a chord in a path or a cycle is an edge between 2 non-consecutive vertices in a path or a cycle. So these are 2 paths in a graph. This is a chorded path because this isn't a chord in this path. It's an edge between 2 non-consecutive vertices. This is a path without a chord. So you can think of a chord in a path as a shortcut. So you can go, instead of going from ACD to AED to C, you can skip D and go directly to this vertex. Whereas this cannot be shortened except by adding a new vertex. So from the definition it's clear that a shortest path has to be chordless. But not all chordless paths are shortless. For example, this is clearly not the shortest path, but it's chordless. But all shortest path must be chordless because otherwise, if it is a chord, you can shorten it by just taking a shortcut. So there's some minimality properties. So shortest path would have minimum length. A chordless path would be minimal with respect to the vertices you visit. You cannot just find a subset of those vertices that form a path. So that's a chorded and a chordless path, and then a cycle is the same if you have a chord between non-consecutive. The chord is an edge between non-consecutive vertices in the cycle. So this is a chorded cycle, this is a chordless cycle. So that's the definition of a chord, and then a chordal graph is an undirected graph with a property that for every cycle of length greater than 3, there is a chord. There are no cycles of length greater than 3 without a chord. So for example, this is not a chordal graph because this cycle in red has length 4 and it has no chord. This is chordal because you can check for all possible cycles that there is always a chord. So it also means that if it's a chordal graph, then also by using chords to make a shortcut, you can always reduce a cycle to a triangle. Right? For example, here you could start with the cycle of length 4 and then shorten it in different ways to triangles. And they're known as, under different names, so one of the oldest terms is rigid circuit graphs, or triangulated graphs, or decomposable graphs, or perfect termination graphs. An important property also is, that's sort of immediate from the definition, is that a subgraph of a chordal graph is chordal, because cycles in the subgraph are cycles in the original graph as well. So that's a chordal graph. Some examples are some trivial examples. Obviously a tree is chordal because there are no cycles. A cactus graph is a graph with no cycles of length greater than 3, so obviously that's chordal. There is an extension of trees that's called K-trees, that's more interesting. So you can construct a K-tree recursively as follows. So the only K-tree with exactly K vertices is a complete graph. And to construct a K-tree with more than K vertices, you start with a K-tree with K vertices, and then you add new vertices, and each time each new vertex is made adjacent to a complete subgraph with K vertices. So for example, these are two trees. So for example, you can start building them with recursively, start with AB, that's a complete graph with two tree. Then you add C and make it adjacent to A and B. You add D and make it adjacent to a complete graph of the existing graph and so on. And this is similar, so you start with a vertex, for example, AB, and then each vertex you add and make adjacent to a complete graph with two vertices. And it's called K-tree because if you do this for K is 1, you get just a standard tree. The first classical theorem about chordal graphs from the 60s is a theorem that characterizes vertex separators in chordal graphs. So a vertex separator of two vertices, V and W, is a set that has the property that if you remove the vertices in that set S, V and W are in different connected components of the graph. So it separates the vertices V and W. And it's a minimal vertex separator for that pair of vertices if no strict subset of the separator is also a separator. So for example, in this graph, if you look at A and C, then X and Y form a minimal vertex separator for those two vertices. Because if you remove those two vertices, the graph is no longer connected, and A and C are in different components of that graph. Or another way to put it is that every path from A to C must pass through at least one pass-through vertex of that separator. So basic theorem about chordal graphs is that a graph is chordal if and only if all minimal vertex separators are complete. So you can, for example, in this example, see that this has to be, this XY separator has to be complete because otherwise there's a cycle of length 4 with no chord. There's no edge between X and Y. And that extends, so that's basically the idea of the proof, but then for separators with more than 2 elements. So this is actually the same graph that I showed, and these are all the minimal vertex separators. And later we'll see you can easily enumerate them and easily find them in a chordal graph. So each, and one thing to notice is that, so these are 2 minimal vertex separators, but you see that this is a subset of that minimal vertex separator. And that's okay, that doesn't contradict the definition of minimality, because the minimal vertex separator, minimality refers to the same 2 vertices that are separated. So this is a minimal vertex separator, for example, for A and F. You cannot find a separator that's smaller, a subset of this, and still separates A and F. This is a separator for A and G. But you can see that they're all connected in this, all complete subgraphs, and that's this theorem. All minimal vertex separators are complete. So second classical theorem is about simplicial vertices. So a simplicial vertex is a vertex with the property that its neighborhood is complete. So all vertices that are adjacent to the vertex are connected. So for example, A is a simplicial vertex because its neighborhood is these three vertices and they're all connected. And in this graph you have three simplicial vertices with this property. Another way to say this, that actually follows directly from the definition and not from Chordal properties, is that if a vertex is simplicial, then its closed neighborhood, so the neighborhood plus the vertex itself, is a clique. It's a maximal complete subgraph, and it's the only clique that contains that simplicial vertex V. And that's almost immediate from the definition, because every clique that contains V must be contained in the neighborhood of V, because all edges in that clique must be connected to V. So if it's the neighborhood is a complete subgraph, then it has to be the only clique that connects V. So for example, this vertex belongs to only one clique, and it's those three. So another basic theorem from 61 is that every non-complete Chordal graph has at least two non-adjacent simplicial vertices. So this one has three, but there are always at least two that are not adjacent. And then the last sort of fundamental results that I will show have to do with a clique tree. So clique tree of a Chordal graph is a tree with as vertices all the cliques in the graph. So here are, this graph has 6 cliques, and those are all the cliques in the graph. So for example, A, B, C, E is a complete subgraph, and it's a clique in the graph. And then a clique tree has a property known as the induced subtree property. If it's true that the cliques that contain the same vertex always form a subtree. So here if you pick vertex E, and look for all the cliques that contain E, then they form a subtree in this clique tree. So if a clique tree has a property, we say it has the induced subtree property, because all these induced subtrees, that corresponds for every vertex in the graph, you have an induced subtree, and they're all subtrees of this clique tree. And so there's also a theorem that says that the graph is Chordal if and only if it has a clique tree with this property. And later we'll see how to find it and how to do this in practice, but this is just the results. So here I show the clique tree, or one possible clique tree for this graph, as just a non-rooted tree. You can pick any vertex as the root of this tree, and then you get the rooted clique tree. For example, like this, if you pick C, E, G, this clique as the root, then you would have this clique tree. So if it is rooted, you can define a parent for each clique, and then you can divide or partition every clique in two sets. You have the intersection of the clique with its parent in the clique tree, and then the remainder. And those two sets are shown here, so these are the two rows in each box. So the top row here is the intersection of this clique with its parent, and the bottom row is just the remainder of the clique. So we call that separators. The top row will be the clique separator, and the bottom row is the clique residual. And then the root doesn't have a separator because it didn't have a parent. And then, so this clique tree is a very convenient structure because it summarizes a lot of information about the graph. So suppose you're given this clique tree with this induced subtree property, then you can actually, first of all, of course, it's easy to reconstruct the graph from the clique tree because the vertices is the union of all the vertices in these cliques, and you have an edge between two vertices if they appear in one of those cliques together. Another thing you can show is that we had this residual clique, so the bottom rows of each clique. Those sets form a partition of the vertex set. So every vertex belongs to exactly one residual. And that follows from that induced subtree property, because if you pick, for example, this vertex E, suppose there is another clique that also contains E in a residual, then because it's E must be an element of every clique on the path between those two by this induced subtree property. So it's also a parent of it cannot be an element of this residual, it has to be in the separator. In any case, so there's a simple proof why these sets partition the vertex set. There's only one, so for example here C is a residual of this clique, that's the root of the subtree of cliques that contain that vertex. You can also show that these clique separators, so the top row, are exactly the minimal vertex separators. So to find all the minimal vertex separators, you can just construct this clique tree, and then you get, from these clique separators, you get all the clique minimal vertex separators, and so on. So an important consequence of all this is that in a Chordal graph, you can have at most n cliques, because these residuals partition the vertices in the graph. Right? So you cannot have more than n cliques, and no more than n minus 1 minimal vertex separators, because every edge in this clique gives you a minimal vertex separator, but some of them could appear more than once. So it's not necessarily the number of cliques minus 1, because some of them could be a duplicate. So the clique tree, in other words, summarizes a lot of the structure in the graph. Each vertex in this tree is a clique, it's a complete subgraph, and it has this important induced subtree property. I didn't explain the construction, but later we'll see how you can construct a clique tree, but for every Chordal graph you can construct such a tree. So the result I mentioned actually necessary and sufficient. It says that the graph is Chordal if and only if it has a clique tree with induced subtree property. And that's related to a more general result, so a more general type of graph called tree intersection graph. So a tree intersection graph is actually defined like this. You take a tree and then you define a set of subtrees in the graph. So here we pick 5 subtrees of the same graph T. It's just a family of subtrees in the graph. And then you can construct a tree intersection graph. The vertices of this graph correspond to each of these subtrees. And there is an edge if the subtrees intersect. For example, R1 and R2 intersect because they have this vertex B in common. So this R1 subtree and this overlap. R1 and R4 or R1 and R5 are not connected by an edge because there is no intersection between these subtrees. So that's a tree intersection graph. And then there is also another basic result that says that all tree intersection graphs are Chordal. So every graph you construct by this in this fashion is Chordal. And then also every Chordal graph can be represented as a tree intersection graph, and we've seen already one way to do this, and we'll see 1 or 2 more. For example, a clique tree is one way of representing the graph as a tree intersection graph. So in this example, the tree is the clique tree. The subtrees in the family of subtrees are the induced subtrees that contain that vertex. And then you have an edge in the graph G if those 2 subtrees overlap, because that just means that there is a clique that contains those 2 vertices. So those are the basic results on Chordal graphs from graph theory. So now we'll see how those objects, so the number of cliques, the clique tree and so on, can be constructed in practice, or give more practical methods for doing this. So the next step will be to add an ordering to the graph. So an ordered undirected graph is an undirected graph with an ordering of its vertices. So you specify an ordering, so a bijection from the indices 1 to n, if there are n vertices to the vertex set. So you give every vertex a number, and that's an ordered undirected graph. And often we'll write this notation: V precedes W if it has a lower number than W. So you can represent an ordered undirected graph just by adding the indices. That's useful. It's also useful to represent it as a table or an array. So if you use this representation, you put the vertices on the diagonal, in the order of the ordering. And then you put dots in the position of the two elements if they're connected. So here A, C, D, B, E is the ordering of the vertices. So A and C are connected. So you put A is connected to C, B, and E. So I put a dot in those rows and columns. So both are useful. So this representation as an array is useful because it's very easy to distinguish in the neighborhood of a vertex which vertices have a higher index or a lower index. And we'll call that a monotone neighborhood. So the monotone or higher, you have two monotone neighborhoods, the higher and lower neighborhoods. So the higher neighborhood of a vertex is all vertices adjacent to it with a higher number. And the lower neighborhood would be everything with a lower number. So in this representation, it's very easy to find the higher and lower neighborhoods. So the higher neighborhood of C is D and E. It's the column below C. And the lower neighborhood would be the row to the left of C. Whereas in this representation, you have to look carefully to actually find the higher and the lower neighborhoods. And we'll use this notation, so the notation for the neighborhood with a superscript plus for the higher neighborhood and minus for the lower neighborhood. So if you add the vertex itself, so you take the neighborhood plus the vertex, and we call it a closed neighborhood. We use notation col for column and row for the closed lower neighborhood because they're the column and the row in this array. And then again, the connection with sparse matrices is that reordering, if the V and E represent the sparsity pattern of a matrix, then the ordering sigma specifies a symmetric permutation of the matrix. So we'll come back to this order. So a graph, an ordered undirected graph is filled or monotone transitive if it has this property, that every higher neighborhood is a complete graph. So you can check that this graph has, with this ordering, is filled or monotone transitive. So for example, the higher neighborhood of 1 is, of course, has the lowest index. So the higher neighborhood of 4 is these two. So the best example is 2. So the higher neighborhood of 2 would be these 3 vertices and their complete subgraph. So in this table, it means that if you have a non-zero or an element in, for each 2 elements in the same column, those 2 elements must be connected. So B and C are connected, are in the closed higher neighborhood for A, so there must be a 0 in the position BC. That's this one. And B and E are connected, so there must be an entry in BE, and so on. So it's called monotone transitive or filled. And in linear algebra, it's actually exactly the graphs or sparsity patterns that have this property of sparse matrices. And that follows from just the mechanism of a sparse Cholesky factorization. So if you have a Cholesky factorization in this form, a lower triangular matrix times its transpose, or if you, as we do here, define the lower triangular matrix to have unit diagonal, then it's L times the diagonal positive matrix D times L transpose. Then L cannot just be any sparsity pattern. It has to have this monotone transitivity property. If you just think about how the Cholesky factorization works. So you must have a property that if in a certain column I, you have entries in 2 positions, 2 rows G and K, then G and K must also be non-zero. So the sparsity pattern is not just any triangular, lower triangular sparsity pattern, it has to have this filled or monotone transitive property if it's a Cholesky factor of a sparse matrix. And then the connection with Chordal graphs is that, so this filled graph as defined like this for an ordered, undirected graph. If that's the case, then you say sigma of the ordering is a perfect elimination ordering for the undirected graph, VE. And then chordal graphs are exactly the graphs for which there exists a perfect elimination ordering. And that's a theorem from 65. So graph is chordal if and only if there exists an ordering sigma for which the ordered undirected graph is monotone transitive. And you can actually see that more or less, first of all, from the fact that this is a filled graph that has this property, you can actually easily prove that it's chordal. For example, if you take any cycle in the graph, and then you have to show that it has a chord if it has length greater than 3. So you pick the lowest index, lowest vertex in the cycle. For example, if you take this cycle, the lowest vertex is this one with index 3. So the two neighbors of the vertex in the cycle must be connected because of monotone transitivity, and that edge is a chord in the cycle. So that shows that if any graph with this property is chordal. And then you can also easily see from the previous theorems that there always exists an elimination ordering that's perfect for a chordal graph. For example, here we've seen this has 3 simplicial vertices. If you pick A as the first vertex, and because A is simplicial, meaning its neighborhood was complete, you can pick that as your first vertex, and then its higher neighborhood is complete. And then you take out that vertex, you have a smaller graph that's still chordal. Again, it has a simplicial vertex. You pick any simplicial vertex as your second, and so on. So that's not the most practical method for constructing a perfect elimination ordering. There exist many algorithms to do this, but it can be done in linear time, linear in the size of the graph, and of vertices and edges. And that also gives you an efficient way of testing chordality. Just try to find a perfect elimination ordering. If it succeeds, then that's a proof that it's a chordal graph. If it fails, then it's not a chordal graph. So checking chordality is very simple. So then algorithms for filled graphs and chordal graphs. So often in analyzing chordal graphs, the first step will be to find a perfect elimination ordering. And we'll use that, for example, to find the cliques in the graph and so on. So an important concept in linear algebra for sparse factorization is the elimination tree of a filled graph. So it's a tree that's constructed very simply from a filled graph. So for the vertices in this tree represent the vertices in the original graph, and the parent of each vertex is the first element below the diagonal. So the parent of A is B because that's the first vertex, or the lowest vertex that's adjacent to A. First parent of B is D, and so on. So that's the parent function in the graph, and that is the elimination tree. So it's clear that the elimination tree doesn't contain all the information about the filled graph. It only shows you the vertices, and then for each vertex, the first element below the diagonal in this array. But because it's a monotone transitive graph, there is actually much more information you can get from this. For example, by monotone transitivity, you can show that the elements in each column below the diagonal must be ancestors of that vertex in the elimination tree. And that follows from monotone transitivity. So for example, these vertices must all be connected, so they must also, these two, C and E, must also be in the monotone neighborhood for B, the higher neighborhood of B, because they must be connected to B. And then these two are in the same neighborhood of the same vector, so it has to be also in the edge in CE. So all the elements in the monotone neighborhood must be ancestors of the elimination tree. So by just knowing this elimination tree, you can reconstruct or say something about this sparsity band. For example, you know that there is no non-zero, no elements in the position HA, for example. In the first column, there is nothing, the element in position H must be 0, because it's not an ancestor of A. We don't know about D. D could or may not be a non-zero. You cannot tell without knowing the entire sparsity. So you can also, another way of thinking this elimination tree is as follows. So you can take this elimination tree and then also add all the elements in this monotone neighborhood to it. So each box here corresponds to one element. So this is each time is a vertex in the elimination tree. So we added the elements in the lower, higher neighborhood as extra row in this elimination tree. So the row above the vertex is just a higher neighborhood. So you can show that this tree is actually another tree representation of the original graph with the same induced subtree property. And monotone transitivity in terms of this tree actually just means that every higher neighborhood, so every top row, must be included in its band. It's a subset of its band. Of course, in practice, usually you work with the elimination tree, not with this expanded elimination tree, but conceptually you can think of the elimination tree as a representation of this expanded tree, and it's just another way of representing the entire graph, because we just take all these columns and arrange them in the tree structure. So this is this induced subtree property. So again, if we take this expanded subtree and then we pick a vertex, for example, this vertex E, and then you look for all the columns that contain E. Now those columns form a subtree of this elimination tree. And of course those columns are also just the rows are given by the rows of C. Right? All the columns that contain C are also the elements in the row of C. So that's another actually representation of the same Chordal graph by a tree with an induced subtree properties. But these are not cliques, these are just complete subsets, but they're not maximal, and they correspond to each column in this graph. As we see later, it will be useful to use the elimination tree and, for example, identify cliques from the elimination tree and the clique tree from the elimination tree without actually knowing the exact sparsity pattern. So that's not possible in general. By just looking at the elimination tree, you cannot identify the cliques in the graph. But if, in addition to the elimination tree, you also know the degree, the higher degree of each vertex. So you don't know the entire higher neighborhood, but you know the number of elements in each higher neighborhood. For example, for this vertex A, the higher degree is 3. There are 3 elements below the diagonal. And then for this, it's also 3 and then 2. So that we'll call a higher degree of a vertex. So the number of vertices in the higher neighborhood. And they satisfy a simple inequality that again follows from monotone transitivity. So if you compare the degree, higher degree from a vertex and its parent, then it cannot decrease by more than 1. So it can be the same or it can be higher. The parent can have a higher degree than the child, but it cannot never decrease by more than 1. So here, for example, this and this have a difference of -1. Here you have a difference of -1, and you can have a higher difference than this. And that again follows from this property that just this higher neighborhood is included in this set. So that gives you this inequality. So now suppose we know an elimination tree for a full graph and the higher degree. So these are the numbers next to each vertex. Then from that information you can actually find all the cliques in the graph. Because first one can show that every clique must be of this form. Every clique is actually one column in this matrix. So it's just a matter of finding which columns corresponds to cliques, and they're called the representative vertices. And then the representative vertices here are in red, and the rule is that actually it's easier to say when a vertex in the elimination tree is not a clique representative vertex, and it's not a vertex if it has a child that has a higher degree that satisfies this inequality, the strict inequality. So if there's a child that doesn't satisfy this with equality, then you say it's not a clique representative. So So here, for example, 13 is not the representative vertex of a clique because it has a child, it has degree 3 and has a child with degree 4. This is a representative vertex because it has degree 3 and it doesn't have a child with degree 4. So by this, knowing the elimination tree and the higher degrees, you can actually identify all the cliques, all the representative vertices in the clique. And you don't have to know the entire sparsity time. So this is, for example, for 5, what we mean by a clique. So 5 is a representative vertex of a clique. That means that this column is a clique. So the element 5, 9, 15, and 16 form a clique in the original graph. Maximal subgraph, complete subgraph, and that's how we can identify cliques. Then something else that you'll need at some point is, again, if you look at the elimination tree with the higher degrees added, then you can actually find from the elimination tree a part of each clique. So for each, so the red vertices are the representative vertices, the starting vertex of a clique. Then you can find a path of, from that vertex to a parent, where the degree decreases by 1 at each step. So you take 4, 3, 2, and then there's no parent with degree 1, so you stop. So that's called a supernode. A supernode with representative vertex 1. And you can do this, find a path like this for every representative clique vertices. So for example, 12, 13, 14, 16, 17, together those form a supernode, because the higher degree decreases by 1 at each step. And then if you, all those sets together form a partition, it's called a supernode partition of the graph. It's not unique. For example, for the same graph, these are two different ways of finding a supernode partition. For example, here you can start from 12 and take this path as a supernode, or you can stop at this point and then add the rest of the path to the supernode with representative 15. So it's not unique, but it exists. Then if you have the supernodes, you can actually arrange the supernodes in another tree with the supernodes as vertices. So for example, this is the elimination tree. If you take a supernode 1, 3, 2, 1, 3, and 4, that's this element. The supernode is just 1 and 2. Then you make this the child of this supernode. And this way you construct a supernodal elimination tree. And then the connection with clique trees is that if you take this supernodal elimination tree that you can derive completely from the elimination tree in the higher degrees, then you can actually, if you know the pattern, actually complete it and get a clique tree. So if you add to each supernode a second row, that gives us the rest. So for the supernode with representative 1, for example, then from the elimination tree we can get this part 1, 3, and 4. And then the rest of that column is the top row of that clique. And you can show that then you get a clique tree, and that's an efficient way of constructing a clique tree. So you need the elimination tree, the higher degrees, and you get this complete supernodal elimination tree. If you actually know the entire pattern, then you can actually construct a clique tree. So that's enough of this. So again, the fact that, important thing that I forgot to mention, the fact that you can identify all the cliques in the graph with a representative vertex, again proves that the Chordal graph can have no more than n cliques. Because every clique is represented by one vertex, and finding all the cliques in the graph is just requires finding all the representative vertices. So then the last part in this first section is on triangularization. So most Chordal graphs are actually not obtained by this triangularizing a non-Chordal graph. So if you take a non-Chordal graph, like this cycle, and you assign it ordering, then you can triangularize it by in steps like this. So you start with the lowest vertex in the ordering, vertex 1. And then you add an edge between all vertices in its higher neighborhood that are not already connected. So here is connected to B and F, so you add an edge between B and F. Then you go to the second vertex in the ordering, and again do the same. All vertices in the higher neighborhood of this vertex that are not connected are connected by an edge, so you add the second edge. In step 3, if you look at the higher neighborhood of 3, there is no edge between 2 and 4, but you only consider higher vertices. So you only consider 4 and 5, they're not connected, so you add this edge. In step 4, you're done, because 4 is only the higher neighborhood of 4 is 5 and 6, and they're already connected, and so on. If you finish this process, you have a chordal graph, because you have a filled graph for this ordering, because you construct it in such a way that the higher neighborhood of every vertex is complete. You can also interpret it in this array representation. So for each vertex, you start with the first one, A, and then if, in this case, the higher neighborhood is B and F, if there is not no edge between B and F, then you add on. And you go to the second neighborhood, here it's C and E. If there is no edge between C and E, you add on. And you continue, and then the end is a filled graph and a perfect elimination order for the graph. And this is a graph model of the gradual fill-in that happens during a Cholesky factorization. If you remember how Cholesky factorization works, suppose you start with the matrix A that's positive semidefinite, a positive definite, has this sparsity pattern. Then there are many different ways of organizing a Cholesky factorization, but one is recursively like this. So you first separate the first row and a column from the rest of the matrix, and then you write it as a product of a lower triangular matrix and its transpose, or a lower triangular and then matrix D and its transpose in this way. So this is a correct factorization of this matrix. You have a scalar on the first element on the diagonal, and then a smaller matrix of size n minus 1. And then you continue, you factor this matrix in the same way, and you collect the triangular matrices, and you repeat this process until you have a complete Cholesky factorization. So then during this process, you look at the pattern of the sum of these three matrices, then the pattern will change exactly as we described during this triangulation. So in the first element, for example, if you take the sum of these three matrices, B has the same pattern as the first column of A, but then this matrix will have all the non-zeros of C, plus non-zeros in the positions, every 2 positions of B where you have non-zero. So if B has a non-zero in position 4 and 6, for example, then BB transpose will have a position, a non-zero in position 4 or 6. So this describes the fill-in during the Cholesky factorization, and that's also why it's called a perfect elimination ordering. So in practice, this is often how chordal graphs are obtained. You start with a non-chordal graph, you choose an ordering, and then you apply this triangularization. And it's often important to do this with as few added edges as possible. And those added edges are called the fill-in. The extra zeros in a Cholesky factorization, or the extra edges in a triangularized graph. It's called the fill-in. If the fill-in is empty, then the ordering you chose was a perfect elimination ordering, and you've shown that you started with a chordal graph. And also sometimes we call this extended graph, so the original edges plus the filled edges as a chordal embedding or a chordal extension. And so if it's not chordal, you're usually interested in doing this with a small amount of fill-in. And then you can distinguish different types of orderings. So a minimum ordering would be one that really minimizes the amount of fill-in, the size of this filled set. And that's been shown to be an NP-complete problem. A minimal ordering would be an ordering that has the property that there is no other ordering that has fill-in that's a strict subset of the fill-in you obtained in sigma. So if F sigma is the fill-in that you get for a certain ordering, there is no other ordering that would have a fill-in that's a subset of those added edges. Then you call that a minimal ordering. And there exist several, and that's actually a very much more practical problem, finding a minimal ordering and a minimum ordering, and you can do it in linear time. Using several algorithms. One of the first ones was the maximal commonality search by Tarian and Yamanakis. So this is interesting to find perfect elimination ordering, because if an ordering algorithm is a minimal ordering, then it will always produce a perfect elimination ordering if one exists. Because by definition, its minimal means it always produces a minimal ordering. So if there's an ordering for which it's actually empty with filling, then it has to find that ordering. So a minimal ordering scheme will produce a perfect elimination ordering if the graph is Chordal, and that's why checking chordality or finding a perfect elimination ordering is a tractable problem. In practice, typically turns out that non-minimal heuristics that don't have this guarantee that they produce a minimal ordering are more efficient in the sense that they often produce a smaller number of filling. So typically, we would use this in practice, for example, for Cholesky factorization. But if needed, you can do a minimal ordering at very low cost. And then the last part of this chapter on Chordal graphs is in practice, because of this, because Chordal graphs are often obtained by triangularization, it's useful to be able to analyze a triangularized graph from the original graph before triangularization, without actually computing all the fill-in and then counting the number of added non-zeros. And that's why these algorithms that I described based on elimination trees are important, because it turns out that you can actually get a lot of information about the filled graph from the original graph and the ordering without actually computing the filled graph. And that includes these quantities. So you can construct an elimination tree for the filled graph without actually computing the entire filled graph, just from the original graph and the ordering. You can compute those monotone degrees, the higher and the lower degree, without actually computing the entire filled graph. We've seen that that's enough to actually compute the, well, if you have a monotone degree, so the number of non-zeros in each row and column, then of course you have the number of filled edges. The monotone degrees and the elimination tree we've seen are sufficient to find all the cliques in the graph. So you don't have to find actually the filled graph to find all the cliques. You can actually do this from the original graph and the ordering and so on. So the complexity of all these questions is typically linear or linear in practice in the size of the original graph and not in the size of the filled graph. So that's important because that allows you to actually compare different orderings for the same non-filled graph and then pick the best ordering before you actually do some expensive calculation. That has a cost that depends on the number of filled edges and so on. And that was why it was important to work with the elimination tree and the higher degrees and not to find cliques and clique trees, for example, and not with the filled graph. So that's my introduction on Chordal graphs. Are there any questions?
So what is the graphs problem? Which edges to remove?
That's a much more difficult question, actually. To do the opposite and a Chordal, that's a very good question. To do the opposite of a Chordal extension, so remove 8 edges to make a graph. But there exist practical algorithms for doing this, even more heuristic. But that also comes up. So the rest of this lecture will apply this to some sparse matrix problems. And that will be the connection with semi-definite programming. So in general, we'll represent sparse symmetric matrices by, or you can represent them by an undirected graph. The vertex set is just integers from 1 to n, denoting the rows and columns in the matrix. And E, the edges, represent non-zeros in the pattern. So for any sparsely parallel Chordal or not, you can define two convex matrix cones. The first one is the cone of positive semi-definite matrices with that pattern. So we'll use this notation, Sn with the subscript E to denote the sparsely pattern, and then a plus for positive semi-definite cone. So for example, if it's a banded pattern, tridiagonal pattern for example, this is the cone of tridiagonal positive semi-definite matrices. The other cone is the matrices with a positive semi-definite completion. So in the tridiagonal case, it would be the tridiagonal matrices that can be extended to a positive semi-definite matrix. So So you can replace the zeros outside the band by other elements that make the matrix positive semi-definite. Or a more faster way to say this, it's the projection on the sparsity pattern of the cone of positive semi-definite matrices. That you obtain an element in that cone by taking positive semi-definite matrices and then setting everything outside the three diagonals to 0. So that's projecting on that sparsity pattern. So we'll talk about these two cones. They're not equal in general. For example, for a very simple sparsity pattern with a tridiagonal matrix of size 3 by 3. So this is not a positive semi-definite matrix. But it's a positive semi-definite completable matrix because you can completely replace the 0, for example, with 1, and then you have a positive semi-definite matrix. So this is a projection of this positive semi-definite matrix on the sparsity pattern. So that shows that those two cones are not equal. It's not positive semi-definite, but it has a positive semi-definite completion. So what are some properties? So obviously they're convex. So one is the first one, the positive semi-definite. One is the intersection of the positive semi-definite cone, the full dense positive semi-definite cone, with a subspace that restricts the sparsity pattern. The second one is the projection on a subspace of the positive semi-definite cone. They're also closed, convex, pointed with non-anti-interior, and for the most part that's obvious, except possibly that it's the positive semi-definite completable cone is closed because it's a projection of a closed cone on a subspace. And it's always true that the projection of a closed cone on a subspace is a closed cone. But there is a property or a sufficient condition that holds in general. So if you project a cone on a subspace, a closed cone, then the projection will be closed. If the following is true, if there's no non-zero element in the cone that you project, that's in the null space of this projection of this general linear operator. And that's true here because there's no non-zero positive semi-definite matrix that projected on a sparsity pattern would give you something non-zero. Because if we project on a sparsity pattern, we set every entry in the position of the edges to 0, but we keep the diagonal, and we set everything in the position where there's no edge to 0, but we keep the diagonal and all the entries that are related or associated with edges. So if you project on that sparsity pattern, you don't modify the diagonal of the matrix. So if a positive semi-definite matrix that projected on that pattern would be 0, that means that the original matrix would have a 0 diagonal, so it would have to be a 0 matrix. So anyway, there's a simple reason why these, the second cone is also a closed cone. So both cones are convex, closed, pointed with non-anti-interior. There are also dual cones, and that's also a simple exercise. If you start with the dual of a positive semi-definite completable cone, so that's the definition of a dual cone. It's all matrices that make a non-negative inner product with all matrices in the positive semi-definite completable cone. So these matrices in the completable cone are projections of positive semi-definite matrices. So if you work it out, it just means that the y is in the dual of this completable cone if and only if it's positive semi-definite. So it's easy to see that the dual of the positive semi-definite completable cone is a positive semi-definite cone with that pattern. And since we already know that these two cones are closed, that also means that the dual of the positive semi-definite cone is a positive semi-definite completable cone. So there are two dual cones and not self-dual as we've seen because they're not necessarily equal. So we'll talk about these two cones actually in, so this is all true for a Chordal sparsity pattern, it doesn't have to be chordal. But now we'll look at these two cones, the positive semi-definite and the positive semi-definite completable cone, in the case where E is a chordal pattern. And we use some of the graph theory of the first part. So some notation, so when I say index set, I mean an ordered list of distinct elements. So it's an index set to describe subvectors or submatrices. We'll use this notation if beta is an index set, then P beta is a 0,1 matrix that picks out that subvector from vector x. So multiplying an in vector with x with this selector matrix P beta just picks out that subvector. So it's a matrix that has just zeros and ones in the right positions to have this property. And if you apply it to a matrix, it picks out a principal submatrix with those index, with the rows and the columns indexed included in the data. So the matrix notation with P beta is useful because the adjoint of this operation is often needed, and we don't have other notation for doing this. If you take an, if suppose beta is an if beta is an index set of a certain length, so if it's length k, for example, and you take a vector of length k, then the adjoint operation will copy this vector y to a matrix of a vector of length n by copying the vectors, the elements of y in the correct positions. So it's the opposite of the extracting a subvector. And the same for a matrix. If you take a small matrix, then you copy it to larger zero matrix, putting the elements of the submatrix of the smaller matrix in those positions. So that's the meaning of these operations, P transpose Y P, or P transpose Y for vectors of matrices. They're the adjoint of extracting subvector or submatrices. So first, again, the connection with Chordal sparsely, as we've seen already in the previous part. So if A is a positive definite matrix with a Chordal sparsity pattern, then we've seen it always has a Cholesky factorization at zero fill. So you can actually find a permutation matrix that represents the ordering in your factorization, so that the Cholesky factors will have the same sparsity pattern as the original matrix. So if A is a matrix with sparsity pattern E, then the Cholesky factor has the same sparsity pattern. And for a triangular matrix, we mean the following, that L plus L transpose has a sparsity pattern. And you can actually show that if a sparsity pattern is not Chordal, then you can find positive definite matrices with that sparsity pattern for which every Cholesky factorization with any ordering has some filling. So that's another very practical characterization of Chordal graphs, or Chordal sparsity patterns. They're exactly the sparsity patterns for which you can factor a positive definite matrix with zero fill. For example, a banded matrix is a banded sparsity pattern is a Chordal sparsity pattern because you can factor a banded matrix to get a lower triangular matrix with the same banded structure. So from now on, we'll just to simplify things, assume that the sparsity pattern is Chordal, but as perfect elimination ordering, we'll just choose the natural order. We'll assume that it has been reordered so that the natural ordering is a perfect elimination ordering. So it looks like this. And then before we often use the higher neighborhood of a vertex, or the closed higher neighborhood. So here we just denote them by index sets, gamma and eta. So gamma is the index sets, gamma 2 for example, are the indices below the diagonal in column 2, including the diagonal itself. So gamma 2 is 2, 5, 7, 8 here. Eta 2 is the strict higher neighborhood, so 5, 7, 8. VR will be the subset of the vertices that are peak representatives. And then monotone transitivity in terms of the elimination tree again implies this property that each column is included in the column, the non-zeros in each column are included in the column of its band, the structure. So the first, that's actually the most important conclusions here for us tomorrow, is a classical theorem about positive semi-definite matrices with a Chordal sparsity pattern. So this is an example of a simple Chordal sparsity pattern. You have three cliques in the matrix. These are the dense submatrices, and the rest is zero. And it's easy to see that it's Chordal because if you think of about what the Cholesky factorization looks like, you'll have a tridiagonal matrix with exactly the same structure. If you factor this with L transpose and L is lower triangle. So this theorem says that if a matrix with this pattern is positive semi-definite, then it can be written as a sum of three simple positive semi-definite matrices. of this with this sparsity. So the first one is just 0 outside this first dense submatrix. The second one has non-zeros only in this diagonal block, and the third one in this diagonal block. And that's if and only if. This is positive semi-definite, if and only if it can be written like this. And then the general notation requires this selector matrices and these index sets. But the general notation expression would be something like this. If you have a choral sparsity pattern, and then in the sum you have as many terms in the sum as you have cliques in the sparsity pattern. And each of these matrices in the clique is a positive semi-definite matrix, but it consists of only one clique in that position. So for each clique in the sparsity pattern, you have a matrix like this, and then you add them to get the general matrix in the positive semi-definite column. So that's useful in optimization for decomposition, because it means that you have a quite complicated convex cone that you can express in terms of a sum of very simple cones. So that's always a useful property, for example, in first order methods, when you can express a complicated convex set as a sum or an intersection of simple convex sets, simple to project on, for example. This is clear. So the proof of this is actually quite easy. So if you just look at this example, so we know that the Cholesky factorization of this matrix will have the same pattern. It will be lower triangular with the same pattern. So each column of the matrix, the Cholesky factor will have this sparsity. You have the first column that's non-zero here. Second column will be lower diagonal, only the lower triangular part will be non-zero in these positions and so on. So then if you write the Cholesky factorization as an outer product of the columns with their transposes, then you can group those outer products in three terms, or in three groups, that give you this with this pattern. So every outer product up to here will have this sparsity pattern, or included in that pattern. And then every outer product of these columns will be having a sparsity pattern that's included in this one. So from a Cholesky factorization with zero fill, you can actually easily compute such a decomposition. And this is the proofs for a general chordal pattern, and you can easily do it using the notation that we described with the elimination tree and the cliques and supernodes and so on. But the idea is exactly what we described. And actually that's true for many questions for chordal graphs. If you can do it for answer the question for a simple pattern like this, or even simpler with just two overlapping diagonal blocks, then that's the most important thing. If you have a question that you can answer for a simple chordal graph like this, then you can easily extend it to a general pattern if you use by formulating it in terms of the clique tree. So the duo of this, so this is for the positive semi-definite cone with a chordal pattern. We also had the other cone where we looked at the matrices with a positive semi-definite completion. And by the duality theory, duality between these two cones, you can actually easily show that from the first result that the matrix has a positive semi-definite completion if and only if all the cliques in the matrix are positive semi-definite. So a matrix with this pattern will have a positive semi-definite completion if and only if each of these principal submatrices is positive semi-definite. And that's again an important property of chordal sparsity patterns. For a general sparsity pattern, that's a necessary condition to have a positive semi-definite completion. Obviously all the dense submatrices must be positive semi-definite, but it's not sufficient. And the proof just follows from duality. If you knowing that this is the dual cone of the first one, and that the first one can be represented like this, it's not difficult to show this. So maybe to finish, we can say a little more about these completion problems. So there's very large literature on all different types of completion problems for symmetric matrices. So maybe the most famous one is the positive semi-definite completion problems. And that is the question that we actually just answered. Given a matrix, a sparse matrix A, find a completion X that's positive semi-definite. So you can replace the zeros in the matrix by any value, numerical value, but you want to do it in such a way that the resulting matrix is positive semi-definite. So for each two vertices that are not connected by an edge, you can assign a numerical value. You want to do it so that's positive semi-definite. Or in other words, you just look for a matrix X, positive semi-definite matrix that has this projection. So for this simple pattern, it would mean find values to these zero blocks so that the resulting matrix is positive semi-definite. So we've just seen for a chordal pattern, the in essence sufficient condition for existence is just that these two blocks are positive semi-definite. And if that's true, it's actually not too difficult to find a solution for this completion problem. If these two blocks are positive semi-definite, then this 3-1 and 1-3 block can be computed from the rest of the matrix, or just feasible values can be computed. And then if you can do it for this simple pattern, then you can work out a recursive method to do it for a general chordal pattern by some kind of recursion of the click tree. You take 2 clicks at a time and merge them, and then reduce your click tree until you just have a single large positive semi-definite click. So algorithms for positive semi-definite completion can be formulated efficiently as a recursion of a click tree or an elimination tree, or supermodel elimination tree, as we discussed in the first part. There is a related problem, it's called Euclidean distance matrix problem. So Euclidean distance matrix is a sparse matrix, is a matrix that has this property. You can express all the elements in the matrix as the squared Euclidean distance between 2 points. So you can find a configuration of points xi, for which in such a way that the aij entry of the matrix A is just the square distance between xi and xj. And that's a problem that's been studied in machine learning, also, for example, in sensor networks. This would correspond to distances between different points on different sensors, and the coordinates of each sensor would be given by a vector xi. There are problems in chemistry that are modeled like this. And in and there's a simple semi-definite characterization of this Euclidean distance matrix cone. A matrix is a Euclidean distance matrix if and only if it can be written like this for some positive semi-definite matrix G. And that's easy to see if you just expand this square in the Euclidean norm. So you get Aij is xi transpose xi, then minus 2 xi transpose xj plus xj transpose xj. So if you define G as the Gram matrix with of inner products xi transpose xj, then you get exactly this relation. So every Euclidean distance matrix can be written like this for some positive semi-definite G, and that shows that it's a convex set and in fact a convex cone. And so then the Euclidean distance matrix completion problem is to do completion of a partially specified matrix or a sparse matrix in such a way that the completion has this Euclidean distance property. And then you have a similar property for the Euclidean distance completion problem as for the positive semi-definite problem. So if the pattern is chordal, then the matrix has an EDM completion if and only if each completely specified principal submatrix of the matrix, so every clique in the graph, defines a Euclidean distance matrix. And again, you can, if this is true, you can quite easily find an algorithm that does this, solves the completion problem for a chordal pattern by first looking at the 2x2 block case and then extending it to a general pattern using the clique tree. And this is a problem that, for example, occurs in sensor network localization. So the given part of the Euclidean distance matrix would be some given distances between different nodes in a graph. And then you're asked to find the distances between other pairs of nodes in the graph for which you don't have the given distance.
But in general, that problem is no linear optimization.
In general, you can have to solve it by some nonlinear. It's a semi-definite programming feasibility problem. So this is the condition. So it's a linear equations plus a positive semi. So in general, you have to solve it as a semi-definite feasibility problem. But if it's a chordal graph, you can actually do it much more efficiently. And the same is true for just the positive semi-definite completion. Has a similar property. Right? If in general, you would have to solve a feasibility problem to do this. But if it's a chordal graph, you can actually do this almost at the cost of the Schwester factorization. Questions on this?
Questions, please.
I can maybe say a few things about the next part, but then we'll finish tomorrow. So this, also because this now becomes, gets us closer to semi-definite programming. We define these two cones, the positive semi-definite cone with a certain sparsity pattern and the positive semi-definite completable cone. So if you want to solve conic optimization problems with those cones as your cones and the conic optimization problem, then you have to be able to compute or define the logarithmic barrier functions for each of the two cones, and you have to be able to efficiently compute their gradients and their Hessians to be used in an interior point method. And the reason why chordal structure is interesting is that all these questions have a very nice, a very tractable answer if the sparsity pattern is chordal. So we'll be interested in the positive semi-definite cone with a given sparsity pattern. And for that cone, we just use the standard log depth barrier. So we know that's a convex, self-concordant normal barrier. But we restricted, the difference here is that X is restricted to this subspace of sparse matrices with that pattern. For example, it's a tridiagonal positive semi-definite matrix. So that's the logarithmic barrier on the space of tridiagonal matrices. So then the gradient of this barrier is defined like this. It's x inverse or minus x inverse projected on the sparsity pattern. That's the gradient of this barrier if you restrict it to the subspace of sparse matrices. So for general, if you just look, that barrier has on the full space of non-symmetric matrices is just minus x inverse, but here you project it on the sparsity pattern if you work on this in this restricted space. So that's the first question. So to evaluate the gradients efficiently, we have to be able to answer that question. Given a sparse positive definite matrix, find the entries in the inverse, but only the entries in the positions of the non-zeros in the matrix X. You're not interested in any of the other entries. For example, if it's a tridiagonal matrix, tridiagonal positive definite matrix, its inverse in general is completely dense, but you're only interested in computing the elements in the inverse from the three diagonals, and not the rest of the inverse. So we see that you can do that very efficiently if it's a chordal pattern, and otherwise it's more complicated. And then the Hessian is similar, so the Hessian is defined like this. If you apply the Hessian of this log dead barrier to a symmetric matrix with the same sparsity pattern, then you have to be able to compute this quantity. So x inverse times that matrix y times x inverse, project the result of the sparsity pattern, and you want to do this efficiently without actually computing the entire inverse of x or the entire product here. Only you want to do it efficiently, only computing the elements you need. And again, you will see that for chordal patterns that's easy. The dual barrier, if this is our barrier for the positive semi-definite cone, then the dual barrier for the positive semi-definite completable cone is just a dual barrier as defined in terms of the conjugate of the Legendre transform. So it's the dual barrier of a matrix S is given by the optimal value of this optimization problem. It's the inner product of you maximize over X in the interior of the primal cone, the inner product minus the barrier of the primal. So that's defined that if you take this as a barrier for the primal cone, positive semi-definite cone, then this value is known as the dual barrier for the dual cone. So to evaluate this barrier, you have to be able to solve this optimization problem efficiently. So in general, it's a convex optimization problem, concave maximization. And for a general pattern, you have to solve it numerically. But you see for a chordal pattern, you can actually do it very efficiently at the cost of roughly a Cholesky factorization. To evaluate the primal barrier for a given x, you do this, that's an easy question. You do a Cholesky factorization, sparse Cholesky factorization, and then from the diagonal you get the value of the barrier. But for the dual barrier, you have to solve this optimization problem. The optimality condition of this problem is given by this. The x that maximizes this as an inverse that has, when projected on the sparsity pattern, is equal to S, where S is the matrix at which you evaluate the barrier. So to evaluate this barrier at a given S, you have to find a solution to this nonlinear equation. Find a sparse matrix X that has an inverse with these specified values in the positions of the sparsity pattern. So that's a given S, that's a nonlinear equation in X, but you can solve it efficiently if E is Chordal, and it's the optimality condition for this. And it also has a nice interpretation. This X hat, or actually X hat inverse, is the solution of this problem, which is actually the dual of this optimization problem. The inverse of this optimizing X is the maximum determinant positive definite completion of S. So you take, in this question here, you take a matrix S in the interior of the positive semi-definite completable cone. In the dual problem, you find the maximum determinant positive definite completion of that matrix. And that gives you a completion Z, the maximum determinant. The inverse of this Z is the X that maximizes this from optimality conditions. But you, in practice, would like to compute X and not Z, because X is a sparse matrix and Z in general is completely dense. And then from this maximum determinant completion, or its inverse, you also get the gradient of this dual barrier, and then you can compute the ratio. So these are all the questions that in general would require solving a convex optimization problem. But if the pattern is Chordal, you can answer very efficiently at the cost of roughly a Cholesky factorization. And I'll discuss that tomorrow. Any questions?
But first let's send people.